So as we move into Module 7.2, taking a look at Chapter 5 in our textbook, dealing with elastic strain, deflection, stability. So within this module here, some of our objectives are to take a look at the design for deformation, talk about strain energy, a little bit on external work, and then get into Castigliano's theorem. So within this module here, some of our goals are to go over the theory related to the topics above, talk about some of these governing equations, go through some practical applications, and then actually do out some problems together by hand. So before we get started, I want to take a look back at an example and do a little bit of review of what we've been talking about up to this point. So in this example here, they tell us we have a bending moment of 2,000 Newton meters. Now this is going to be applied to a solid shaft, so we know the shaft is solid, and it's going to have a 40 millimeter diameter. Now, the next thing they want us to do is replace the shaft with a hollow version with an outside diameter that is 1.15 times the inside diameter. Now, they must have the same outside surface stress. So that's how we're going to relate the two, the solid and our hollow shaft, is by this outside surface stress. So this is a little bit different the way they give us this information. I think this is important to understand that not every problem is going to go through the exact same way and ask for the same exact things. So looking at it in a different way. So now we have to compare a solid shaft and a hollow shaft right there. And even within the hollow shaft, they tell us here that this is outside diameter is 1.15 times the inside diameter right there. So that's another thing that we're going to have to take into account in how we're calculating the thickness of the wall and everything else as far as our dimensions go. So as we go to solve this problem out right here, the first thing we want to do is write down everything that we have in the problem statement. So we create our setup page right here. So our given information tells us that we have a moment of 2,000 Newton meters and a diameter right here of 40 millimeters, which I want to convert right away to meters. So this is equal to 0.04 meters right here. So now I have two different situations. I have a solid and a hollow. So in the solid, that's my D right there. On my hollow over here, this is my D right here. On my hollow over here, I have a D inner and a D outer, and I know the relationship between them is that 1.15. So as we begin our solution, the first thing we want to do is take a look at that given information and go back into our text, our notes, and discover what is our governing equation. What can we use as our governing equation? Well, let's talk about the solid bar first, one at a time. So for the solid bar, I'm going to relate back to chapter 4 in equation 4.6. And this is going to carry through the entire semester right here. Just because we saw in chapter 4 doesn't mean we're done with it there. It's going to keep coming back. So this is equation 4.6 there, where we have this relationship here that our sigma is equal to m times our y, which is the distance from our neutral axis is what our y is, all divided by our I value right there. So I like to, off to the side over here, write down what I know. So I can go back to my appendice right here. So again, with the design course, as compared to some of your other courses, not everything is given in the problem statement. As we saw with this one here, it was pretty minimal what they gave us. But from the wording in that, and from what we know in that, looking at this setup page here, we need to know where to go to get the additional information that we need to solve this problem. So we can go back to our appendix right here. So we see we have this I value right here, and this is for a solid round bar. This is why I solve for these separately and dealing with the solid bar first. So if I'm talking about this solid round bar, I can go back to my appendice here, look up that shape right there, and find that my I value here is going to be equal to pi times d to the fourth divided by 64. Now my y, which is the distance from the neutral axis, is going to be the diameter over 2. Now, why is this the case right here? Well, because if the distance from the neutral axis, that's the radius right there. What is radius? Radius is half your diameter. So the neutral axis is in the middle right there. So that's really measuring our radius rather than our diameter. So when we say y, it's going to be our diameter, which they've given us in the problem statement, a d value right there, divided by 2. That's what our y is. So that's, again, why I made these little notes right here, so I understand exactly what I'm doing as I'm writing out all my values right here for each of my variables. So y is the distance from the neutral axis, which in this case here for a solid steel bar or solid round bar is going to be my radius, and radius is equal to my diameter divided by 2. So there's my y right there. And then I also have for my problem statement, my moment is given to me as 2,000 Newton meters. Pay attention to our units, and my d is equal to 0.04 meters. So now you notice I converted from millimeters to meters already for this right here. So this is now in meters right there. So now that I have my governing equation, and I've kind of made a little side note over here for what all my variables and all my values are to plug into my governing equation, now I can actually go through and start plugging them in. So I say, okay, plug in my values right here. Well, there's my governing equation from 4.6 is equal to my sigma is equal to my my all over my I value. Well, my I value is what I just grabbed from that appendix in the back of the book right there. So this is equal to pi d to the fourth over 64, and I have on my numerator right here my m times my y right there. So I can start rearranging slightly, and I just change things around here. So you got the 64 on the bottom, I move the 64 to the top right there, and I start changing things around. Well, I got 64 right there, now divided by this 2 right here. Let's just get rid of that, change this 64 down to 32 right there. Well, I have a D up here, and I've got D to the 4th down there, so I can cross that out, and this is now D to the 3rd on the bottom down there. So all I've done is reduce and simplify my equation. So before plugging in our numeric values, even though we could plug in directly to this right here, especially if we're doing this by hand, let's simplify it down, see what cancels out, do our unit analysis, rearrange things, and simplify first before we plug in and make our work more complicated for ourselves. So we plug that in now. We have this is sigma is equal to 32m over pi d to the 3rd when we've actually simplified this down. So now I can plug in my value for m right here of 2000, and I can plug in my value for d right here, which is 0.04 in meters. So again, Newton meters and meters. Pay attention to your units. Do out your unit analysis. We'll do that out right there, and I actually plug this out, plug into a calculator, solve by hand, MATLAB, whatever your choice is. I find that my sigma is 318 megapascals. So this is solving out the first part of the problem right there, just to get my sigma right there. Then the other thing I want to note right here before we move on is the fact that let's just say we didn't simplify this down. Let's say it was even more complicated equation than this right here. Well, you do have the option of programming this into a numeric solver. So even if it's Excel or MATLAB, something simple like that, you can plug this in as it is there, and you can have all these values defined for these variables that we have over here. So we can have this all off to the side, and we can even have a separate one. Let's just say we're doing Excel, and we had our I value right here. Maybe we have I, and we have this equation plugged into an Excel block right there, and we can say, well, my D is equal to this, and I can plug it right in, and therefore my I is equal to this. And that's even something nice if for a problem like this, we had to vary our D or find for different values, different diameters, things like that. Well, then we could plug it in, run a little loop, run a little pre-recorded macro, depending on what program we're using right there, and have it cycle through. Whereas if we had to do that by hand, even with the simplification, to run that through by hand every time would be a lot. So if we're talking about a lot of different diameters, and this is not just a theoretical problem, this is reality. So let's just say we needed to be within a certain stress for a design project. And we wanted to say, well, what is the minimum diameter that we could do to be within that range to get our stresses according to our specifications. So that's one right there where we could write a little program that runs it through, and maybe we do diameters every 1/10 of an inch, every millimeter, whatever it is, and we run it through a range of those, and we say, oh, okay, now I'm looking at this, and then I have a whole chart I can look at. Okay, this for these diameters, these are my stresses. So I can look at it and say, oh, okay, well, between this diameter and this diameter is actually going to be good for my design process. Side note to that, make sure we've taken into our safety factors as well as we're thinking about those. So we're looking at that stress right there. Make sure it's, for whatever safety factor it is to be designed to be used for its unintentional use by your client in the end. So just a little side note with that there. But going back to this problem with this is really a good example from a simple governing equation right here when we started with equation 4.6 of how we could plug in different values for that D. And we can see here, even with this, our Y is a function of D, and we have our D down here in our value for our I value right there. So really, we can back our stress out just by plugging in different diameters. So if we're looking at this for one type of material right here, or round bar, and we want to say, how does my stresses compare for different diameters? I could do that. I could write that out. And again, that's a simple one in MATLAB. We could write a simple script that actually runs through the loop right there. And we could even write contingencies into that there that says, if it's less than this, spit it out, good, or whatever it is. Or in Excel, we could just have a list, a whole chart of those showing our different diameters for those different stress values. So now that we've gone through and solved for our stress for the solid tube or solid shaft, now we want to go back and look at it for our hollow tube right here. So we still use that same governing equation, equation 4.6 from our textbook there, which says that sigma is equal to my over I right there, where now we go back to the appendices in the book, but we're dealing with a hollow shaft. So this is a different equation for our hollow tube right here, where I is equal to pi over 64 times d outer to the 4th minus d inner to the 4th. Where our Y value is our D outer over 2. So now it's our D outer over 2 for this relationship here. Our M still stays the same as 2,000 Newton meters. Now our DO is equal to 1.15 times our DI. So our DI is equal to DO over 1.15. So that's our relationship there. But I want to specifically write these out as those values right here for DO and DI. So it makes it easier when I plug back into my governing equation. So I can go back to that governing equation there, and I can put on the bottom here for my I right here of that value from our appendix C for a hollow tube right there, which is pi over 64 times the difference in our d outer to the fourth minus d inner to the fourth right there. And on the top, I have my moment times my y value, which my y value was my d outer, my outer diameter, divided by 2 right there. So now this is my governing equation right there, and I want to simplify this down the same as we did in the first step for the solid one. So we can say, well, I still have this 64 if I move this up to the top right there. So I have 64 over pi right there, and I can say, well, I've got my 64 and my 2 here. Let's cancel that and bring that down to a 32. So that reduces down to our stress is equal to 32 times our d outer. Make sure we're paying attention to d outer and d inner, times our m value right there, all over pi times d outer to the fourth minus d inner to the fourth. Well, let's get this down. This is two unknowns in one equation right there within the right side of this right now. Three unknowns total if we're talking about our stress at this point. And now we want to say, well, let's get this in terms of our DO. So what is our DI in terms of DO? Now we can go back at the relationship in our problem statement that DI is equal to DO over 1.15. I can plug that in there now. And now I can say that my stress is equal to 32 times my DO, my outer diameter, times my moment, which I know is 2,000 Newton meters from up here. Plug that in. All divided by pi times my d outer to the fourth minus, now I've plugged in di relative to do right there, which is do divided by 1.15 to the fourth right there. So now the only unknown on my right hand side of the equation is my do. So let's solve this for our do, or our outer diameter. So now that we have that equation there, the thing that we want to think back about is we talked about how this technically at the beginning had three unknowns and one equation. So three unknowns were my do, my di, and my sigma. Well, we took care of one of the unknowns by relating our do and our di by this relationship that our di is do over 1.15. So now we've got two unknowns in one equation right there. So our other unknown I want to deal with next right here is our sigma. Well, if we go back to our problem statement, the stress on both the solid shaft and the hollow tube were going to be the same. So they're both equal to that value we found for the first part of our problem right there. We solved for our sigma for our solid shaft, which is 318 megapascals. So now we have one equation, one unknown. Our only unknown is our DO. So the next step is to go through and solve this for our DO. But we notice we have two DOs on our denominator and one on our numerator, so it's going to take a little bit to rearrange this. So first thing I want to do is take this denominator right here and let's multiply it over to this side right here and get it like that. So what we have now is we have 318 times that denominator, which is pi times DO to the fourth minus DO over 1.15 to the fourth right there. It's equal to our numerator right there, which is 32 DO times our 2,000 Newton meters right there. So next, let's say, okay, let's get our DO by itself right here. So let's divide both sides by 318 pi right here. So get rid of this, move it over to this side over here, divided by 318 pi right there. So we can simplify that down a little bit. And we say, okay, well, what do we have here? Well, let's get this DO out of this side and put it back over here. So we're going to divide our DO by both sides right there. So combining those steps right there, I now have, now that I've eliminated this from this side, I just have my DO to the fourth minus DO DI to the fourth right here, this relationship right here, divided by, I'm going to divide my DO right here, divided by DO there. And then over on the right side, when I've moved this over, my 318 pi over here, I can move that up here. So it's 32 DO over 318 pi right there. Now what I can say is this is times our 2,000 right there. So with that right there now, I can say, well, I can look at this and simplify this down a little bit, rearrange these DOs, and we skip a couple steps right here, but we can take a look and say, well, these are the fourth, I have this 1.15 to the fourth. Make sure we do all that math correctly there, and we end up with is our DO is equal to 0.053 meters. Now this step right here with even divided by the DOs is a little bit complicated, but yes, we can do this out by hand. We do need to make sure we pay attention to our units as well as our decimal places here as we're doing this out to keep track of things. This is also another one where maybe we do want to move to a numeric solver. Maybe we want to plug this into MATLAB. Maybe we want to use Mathematica, Python, Excel to do that there. But we do this out here, and you can do it out by hand, and we end up with our DO of equal to 0.053 meters. So with that there, we could then plug back into our relationship that we have and solve for our DI, and we could get all that information that we need for our hollow shaft based upon the fact they both have the same sigma value as our solid shaft and our hollow shaft. So now we'll move on to chapter 5 in our textbook. We're going to take a look at strain energy methods and buckling. So as we jump into this, a little introduction to this chapter here, a couple different things we're going to be looking at. We're going to be looking at elastic strain, deflection, stiffness, and stability. Now these things are all considered of basic importance to an engineer. So why I want to bring this up right now is as we talk about this design process right here, these are things that we want to consider, especially as we're moving on to the stage where we're doing some of the testing and evaluating different materials and material properties right here. These are things that we're really going to want to consider and figure out, how do we test this? How do we look up this information? Is this something I could do with FEA? Is this something I need to do some tension testing, some hardness testing, some fatigue testing, life cycle testing? How does this come into play with what I'm working on for my part or project or design? So as we're looking at this, one of the things we want to talk about here is deflection versus stiffness right here. If we're looking at this, if we're dealing with deflection or stiffness right here, rather than our stress right here, it's often the controlling factor in the design of a part. So as we're thinking about deflection and stiffness right here and how those two are related, rather than looking at our stress, well, one of the things that we want to consider is one's easier to measure than the other, especially if we're talking about experimental data. So if we're looking at our deflection or our stiffness of those right there, that's something that we can actually run a test and see. So deflection test, we could do some of these different tensile testing methods right there. We could even, maybe it's the 3-point bending method we're taking a look at, all those types of things, and we can get that information from our deflection and stiffness from experimental data right there. Whereas stress is going to be something we calculate based upon some of those values we get for deflection and things like that. So we got all goes back to our stress strain curve, and we're looking at the slope of that curve right there. Well, we may have measured the actual deflection, which equals the strain on our x-axis. If we want to get the stress out, maybe we already know that modular elasticity, and we can back that out of that there for a known material. So things to think about like that right there. And that's why oftentimes this is a controlling factor in design of a part. As we're looking at our deflection or stiffness, we still may be concerned with stress, but maybe what we can actually measure and actually get information on is going to be this deflection or our stiffness of our part or our beam, whatever we're looking at. Now, how does this relate? Here's a practical example. Maybe we're looking at a machine tool frame right here. So if we want to maintain manufacturing accuracy, this must be extremely rigid. So this is why also they're really concerned not only with how we're going to calculate this and how we're going to measure it, but also the fact that we're not really concerned about the stresses in it. We're more concerned that it doesn't move. It doesn't change. It doesn't shift. So we're really not concerned how much stress is in it, as much so as we're concerned with, is it going to move? Is it going to deform? Is it going to stretch? Is it going to change its shape? And if it does change its shape, how does that affect our product as a whole? So in this case here, if we're talking about machine tool frames right here, you can't have that move at all. If the accuracy of that is crucial to that machine right there. So if you really want to take a look and make sure that there is almost no deflection within the expected loads and usage that we're going to be using this at. So that's something that we really need to consider, again, as part of a design project right here, sort of the design of our project or part right there, and why this is a controlling factor, especially for something like this right here, where that is crucially important, that does not move at all. It does not deflect. It does not deform at all. It needs to be extremely rigid. So that's just one example right there of why deflection as a measurement right there and as an output right there for what we're looking at might be more important than our stresses. Now, that's not to say the stresses aren't important. We don't want this thing to fail and crack over time. We got to look at all of that, but this is saying this is going to be more important. It's going to be the controlling factor right there, is that it doesn't deform at all. And once we have that information, like I mentioned above here, we can go back and calculate our stress and take a look. Oh, okay, yeah, well, it still does come within our stress specifications that we want for this project, for this part, for this machine right there. But more importantly, we really need to make sure it didn't move at all, it didn't deflect or deform. And that's exactly what we talk about in this next section right here. When these frames are made massive enough to satisfy those requirements there, that it doesn't deform and it stays rigid the whole time, oftentimes these stresses are going to follow right there, and they're going to be insignificantly low from that there. So this is not necessarily an afterthought, but a secondary consideration, I would word it as, for this right here, when we're talking about dealing with our deflection first as the controlling factor, and then taking a look and still considering our stresses, but they're most likely, the way we're designing, it's going to be very low and something we still need to double check, but after we've already made sure that our deflection and deformations, and this is made rigid for our first criteria, our controlling factor. Now moving on to the stiffness part of this may be a tough example when we're dealing with vibrations right here. So if we need an incredible stiffness right here to eliminate the vibration problems. So this is often important in a lot of medical equipment, ultrasound equipment, and certain things within hospitals where you really can't have any vibrations at all. Could affect the measurements, could affect the machine itself, could affect the electronics within the machine. So we want to make sure that our parts, maybe it's the base or the case for this right here, have that stiffness requirement in order to eliminate any of these vibration problems. And last, we did talk about deflection and how it would relate to manufacturing for machine tool frames right here. Well, here's another example where deflection is very, very important. It could be our controlling factor right here. Is if we have multiple parts within a system. And if one deforms, the whole system fails. It doesn't interact the way it should. So a great example of this is gears. So if we're talking about gears and all of a sudden one of the gears or two of the gears deform, all of a sudden they lock into place because they've expanded too much and then the whole system doesn't move, it binds. Or maybe the opposite of that, it contracts a little bit right there, it shrinks up and it moves away from each other right there and they don't engage anymore. The teeth start slipping within the system right there. So that's where this deflection really becomes the driving, the controlling factor right here more so than the stress. Yes, we're concerned with the stress of the individual gears and all the parts and materials of that right there, but if the deflection is so great that it doesn't function as a system anymore, then it doesn't even matter at that point where the stress is because the whole system has already failed. We need to redesign it. So if we get the deflection right so that the system works together for this gear situation right there, then what we can look at, okay, now that we know that the deflection is going to be minimal, it's not going to interfere between these individual components or individual gears, then we can go with that and continue on and back out, again, our stress values for those gears as well. So this is more, again, thinking of things that we've seen in ME14 and some of our other classes right here, but applying them to a design criteria. We're really thinking of, it's not just this final part, it's how this final part plays into the whole system. And then we're thinking about all these different things and like, well, yes, stress is important, but maybe we really need to consider that it can't deform or that the stiffness needs to be a certain amount so that there's no vibration. So we're thinking not just about the part individually, but the system as a whole, the project as a whole. And that's one of the main things to really consider when we're talking about design right here, is we're not just one individual element. Even if you as a design engineer, and that's your job, is design that one individual element, all the specifications for that are coming in from the system as a whole, from another team of engineers, from a funding agency, from your company, whoever it is, and those all come into play for us here. We really need to consider all of those in the design process right there. So that's what we're talking about right now. This is just getting into these things we're measuring now: elastic strain, deflection, stiffness, and stability, how they're related to each other, why these are important, and talking now about this controlling factor and how one thing may be more, maybe the controlling factor and be more important to calculate first and then consider everything else. So now this leads us into our discussion of stresses right here. So this is another important aspect of our elastic strains, which comes from our deflection measurements there as we calculate our strain right there and our displacements. So how these strains are involved in experimental techniques for measuring our stresses right there. So we get our strains right there and then we can get our stress calculations right there. And even though these stresses are not necessarily a directly measurable quality, well, strain is. So we can experimentally measure our strain values to get our stresses, and stresses are still important. So when we're talking about elastic constants of known materials, so if we know what these elastic constants are, then experimentally what we can do is we can come up with our strain values, which can be just transported into our corresponding stress. This is just using our stress strain curve, our elastic modulus right there. If it's known what our elastic modulus is, we know from Hooke's law that we have a relationship between our stress and our strain by our elastic modulus right there. So that means we can take a look at these values by means of our stress strain relationships. Now this may be something you do a hand calculation, numerical analysis of this, or you might just be looking at the output data from our raw data. If we're doing a tension test right there, we might have our force versus deflection that we convert into a stress strain curve. Look at that stress strain curve and maybe we take and measure off of that our elastic modulus, and one, maybe we're comparing to make sure, yes, it is the material that we say that we put in there and that it does have the values that we'd expect from our lookup, from our material properties or from our manufacturer. Or maybe something where we do that experimentally and we find, okay, this is our elastic modulus right here. We need to find what our stress is. So if we plug in that value for our elastic modulus right there, because we know the material, so this is an example right here, we know the elastic constants of that material right there, so we know the slope of that line, and we've measured our strain, then we can back out our stress. So that's a couple different ways that we can do that, but this is something to think about with our stresses. Even though they're not directly measurable, strain is, and there's a lot of ways that we can go from our strain to get our stress values right there. So now let's talk a little bit about this design for deformation. So if deformation is going to be our controlling factor, the thing we're really concerned about for the design of our product right here, let's take a look at that and take a look at some governing equations and some of the theory behind this and how we actually design for deformation. So if we define a maximum amount of deflection for an element, this is a really general way of saying, okay, we know the absolute maximum amount of deformation or deflection that we can allow for our individual part or product that we're designing before it doesn't function. It becomes unacceptable for one reason or another. So if that is the case and we know that amount of deflection, so let's just say we go back to those 2 gears and we say it's more than 1/10 of a millimeter, and then the teeth won't engage, or then it'll bind it up too much like that. Or if it's for a machine frame again right there, then we can take a tool frame right there, we can take a look and say, well, if it goes more than, a micron, that's going to be way too much deformation for us right here, and too much deflection, that's not allowable if it's any more than that. So for any of those cases, specific cases right there, we would have a value for our delta max right there. So from that there, what we could do is we could use this relationship we've seen before between our load, the length of our member, the cross-sectional area, and our modulus of elasticity, it's known right there, and we could back out whatever one of those it is. So maybe what we can say, well, if we're dividing for deformation right here, and we know our deflection for this case right here, and we know our, let's just say we know our max load that we're going to be putting in here, that we're going to be using for this here. We know the material we're going to use, and we know what we don't know maybe is this information for the dimensions of it. This is just an example right here. Could have been a different way, but we don't know the length of it or a cross-sectional area. So that's something we're going to design. So our design process right here is not the material, because we already have the material information. We have our elastic modulus from that. We already know the max load because we know the practical application we're using this for. What we really want to do is say, okay, with that material, what dimensions do I need to make it in order to stay less than our max deflection right here? So that's where we can use this relationship right there and say, okay, well, we'll go through and we'll try a couple different ones out. And this, again, is a great opportunity to really start getting into some of these numeric solvers. So we want to find that value right there that is going to be just less than our delta max right there, but still having, let's just say, our cost and weight to keep it down right there, which are always two big factors: cost, weight, and size. So we want to keep those minimal. So we want to make that L and A the smallest we possibly can, but to keep this under our max deflection right there for this problem right there. So we could go through and we could go, take a rough guesstimate and start there and do it by hand and keep going through and through until we get it, just at that right thing. Or we could write a little macro, or we could write a little loop in MATLAB, and we could go through and solve this and say, well, L and A are going to be related, and we might have, if it's a certain beam or a shaft, whatever it is right there, we can plug in the value for a cross-sectional area based upon those dimensions right there. And we plug in those two dimensions and run them through every millimeter, every micron, whatever it is. And we do that until we get out our delta max right there. And then we take a look back and look at our combination between our L and our A right there for that value right there that fits in perfectly for our max deflection. So that's, again, another way we can kind of tie this into a numeric solver to get that just right, to back out our L and A for our known value right there. Now, this could be another way right there where maybe we already know our dimensions of this right here, and we want to pick our material. So we need to figure out, we need to back out an elastic modulus. Or maybe we know all the elastic modulus and the shape and size of it right there. We want to figure out, well, based upon this, and we know we can only have this maximum deflection, what's the max load this can take? And is that acceptable for whatever system or part that we're dealing with right there? So a lot of different ways we can use this one simple equation right there based upon designing for deformation, where this is a known value for our delta max right there, to get out what is our load, what is our length, what is our cross-sectional area, and what is our elastic modulus. Now the same could be said if we're dealing with shafts and torsion. We still have this relationship over here. We're still trying to design to remain below this level right there. So in this case right here, maybe we know our torsion and we know our modulus of rigidity right here. Then we need to calculate our L, and we can look up our relationship for J for this right here and L, and we do the same thing we did up here, but now we're dealing with torsion rather than just an axial load in this case right here, and we need to back that out right there. Or maybe we know what the torsion is, we know what the torque is applied from the motor and the generator, and we want to figure out for this shaft right here, well, in order to stay below this level right here, our max level right there, what the dimensions of that shaft need to be. So that's another example that we could use right there if we're dealing with torsion rather than an axial load. So let's discuss a little bit more realistic situation right here. So we're still considering our design for deformation right here. But what happens in reality is there's not always just going to be one load, like we saw in those previous relationships, those previous equations there. So what happens if we have more than one load present at the cross section right there and along the length of the element right there? So if we have a load n at some distance x right there, a torsion at x, a moment at x, a shear at x right there, at some distance x along the way right there. What if there's more than one load present at this cross-sectional area? So then we can go back to what we talked about before in this course, along with our ME14 course, and look at our method of superposition. And we can talk about this. What if there are many elements forming the system right here? So not only are there more than one loads at the cross section, but there's many elements within the system right there. So this is, again, we're designing this not as an individual part, but as an entire system. And this is the case. There are going to be more than one element for most cases within the system right there. So if we're thinking about designing for deformation, not only do we want to think about, okay, what happens if this part deforms too much? Or what is the maximum amount of deformation I'm going to allow for this individual part? Well, then we need to say, well, how does this part affect the rest of the system, affect the next part in line that it works together with? So that's when we're thinking about designing this as a system rather than an individual part. That's where we need to really consider that there are going to be many elements forming the entire system and not just one. How do they all interact? How do they all work together? So let's think about this right here again. So go back to the top part right here. If there's more than one load present, so this is almost always going to be the case in reality, that there's going to be more than one load right there. And again, we can see right here, are we talking about it's not just going to be this axial load. So let's just say, take a really simple application right here, and it is one column that we're designing that is going to hold a water jug on the top of it. So in theory, you have something, like this right here. We have our column right there, and then we've got some load being applied to the top of it right there. From our water jug. So we're just designing a stand to hold this water jug or this vase or whatever it is right there. So technically, this is just right here. This is our only one load that we're going to have to design this for, and we could use that one simple equation. But in reality, let's just say it's kind of like I drew it. It's not perfectly straight, because this is a great example of me trying to draw this right here with my mouse. I'm not going to make it perfectly straight. Same type of thing if I'm trying to actually machine and make this. Is it perfectly straight? Or is it maybe there is a slight angle to this right here? And then all of a sudden this load is not a purely axial load, and all of a sudden there is a bending moment as well on this. Something like that there. Or maybe there is a little bit of somebody comes and pushes it from the side because it's going to be used outside of its intentional use right there. So then is there all of a sudden, are we thinking about if this is fixed to the ground right there, is there a shear force right there? Or maybe somebody twists this a little bit and we're turning it rather than that as they're trying to move this in the room, and then they apply a torque. So potentially somebody just trying to move this or bumps into this, all of a sudden we have all four of these and not just this pure axial load on the top. So now a simple case right here where we're just one column, one material to hold a vase or a water jug or a weight of something on the top of it, goes from it was just an end load right here, an axial load right there. Well, now we've got torque because somebody twisted it. Now we've got a moment because it's not perfectly built straight, and now we've got a shear right here because somebody bumped it from the side and it's fixed to the ground. So it is practical to consider all of these, and the fact that we're saying that there's going to be more than one load present at a cross section, where maybe again we do our method of sections right through here, and we're looking at this all the way up, different sections right there, and we see where we have that deformation. Well, now we're going to have to consider all of these right there, and that's where we go back to that method of superpositions when we do this. So next thing I want to take a look at is energy. Now, as we've seen before in previous courses, our work is equal to energy right there. So we have this relationship that we've seen before, where we need to consider that work done by external forces in moments deform elements. So there's going to deform elements within whatever part that we're looking at right there, and that's going to generate internally. This is going to generate axial loads, moments, torques, and shear forces, all internal to our part right there on those elements right there. So that's something to consider, is as we're applying these external loads, we also need to think about what it's doing internally to our part or product. So with that there, we can now say that the work of this N M, T, and V right there, axial loads, moments, torques, and shear forces right there, is equal to our potential energy right there. And this is also then going to be equal to our strain energy right there. So now we have a relationship between work and our strain energy right there. We can write this out now that U sub E is equal to our U sub I. So we're talking about strain energy right now. We're going to have methods to determine the normal and shear stresses due to all of those, our axial loads, our bending moments, our transverse shear forces, and our torsional moments right there. That's how those are all going to come into play towards our strain energy like that. So what we can do is we can calculate the strain energy from the external force or the moment. So because this external force or moment then creates these internal forces as well, our axial loads, bending moments, transverse forces, and torsional moments as it deforms those internal elements right there, therefore we can then calculate the strain energy from our external moment or force. So now I want to move on and take a look at table 5.3, which is going to relate back to all of this right here as we're talking about our strain energy right there. This is a summary of energy and deflection equations for use with Castigliano's method right here. So what we can do is we can take a look at each of those different load types that we just discussed right there. So there's our load type, there's our axial, there's our bending, there's our torsional, and there's our transverse shear right there. So again, our axial, what factors involved, what variables are using. So this right here is going to have our load P for our axial load there, elastic modulus, and our cross-sectional area. Then we have bending, we have our M right there for moment, our elastic modulus, and our I value right there. Then we also have for torsion, we have our T value, our modulus rigidity, and our K prime value there. And for transverse shear, we have our shear force V, our modulus rigidity, and our A value right there. So with that right there, those go into our energy equation. So we have here our energy equation for special case where all three factors are constant with x. So they're not going to vary with distance, which is a special case and not a realistic situation technically right there. So then we have these relationships here where we can get that strain energy right there. We can get our U value right there based upon our factors involved over here. In this case, our load. We can see there's our load right there. There's our length right there, our dimensions. There's our E and our A there. Whereas if we're dealing with bending, there's our moment and our I value. Torsion, we have near our T value and our K prime value. And then for shear stress, we have our V and our G right there that we see in those equations there. We also have down here, the second part of this table right here, for each of these, we have our general energy equation, and we also have our general deflection equation for each of the axial, bending, torsion, and transverse shear as well. So this goes back to table 5.3 in our textbook. So if we want to take a look at our strain energy for N right there, let's relate this back to our normal stress. So if we recall for what we have down here in our diagram right here for normal stress, we see there we have our applied axial load N right there, some cross-sectional area A, some distance away here, and here's our stress at that element, that distance away in our x direction. So that's exactly what we have is we have this relationship here that sigma sub x, our stress at this point x along our x-axis right here where they have this cross-sectional area A is equal to this applied load. There's our normal load right there, divided by that cross-sectional area at that point A right there. So how does this relate to strain energy? Well, we can see that our strain energy is going to be equal to the integral right here of 1 over 2 times our modulus elasticity times, there we go. There is our normal stress in our x direction squared dV right there when this is integrated over V right there. So now we can plug in this relationship for N over A right there because this is our sigma, so plug this in right here for our sigma x squared right there. And now what we have for our strain energy is we have this, our U is equal to the integral when we plug that in here of our N squared all over 2EA squared right there. So this is just our normal load right there. There's our modulus elasticity, there's our cross-sectional area right there when we take that integral. So this is how we get the strain for a normal stress right there for our axial load N. Now, if we want to talk about strain energy for an axial load N right there, one thing we want to consider is that the stress is going to vary with the length right there. So it's going to affect right here, we're going to have this differential volume that we see in this relationship there. So if we have that, in this case right here, we have that our strain energy right here is equal to the integral that we just saw on the previous slide right there over V of our N squared, of our, that axial load squared all over 2E A squared dV. Well, dV is going to be equal to A dx right there. So we can plug that in and we see that right there. Well, we can remove change this around a little bit right there, and if it was ADX right there, this is going over the length now. So this is the integral over the length from the 0 to the total length L right there. Now this is again dependent in the x direction right here, n of x, wherever you're moving along that length right there, squared all over 2EA dx. So rather than being dV right here, this is now dx right there. So rather than volume, we're dealing with our length term right here. And this again is because the stresses are going to vary with length. So by defining that differential volume right here, we've now related it back to length, and we can say, okay, as we go from 0 to the total length of this, we can look at that strain energy at each distance of x along the way. Now, if it's constant along the length, then we can reduce this down and we can have the same relationship that we've seen here, that our strain energy is equal to axial load squared times the total length right there, all over 2 times the modulus of elasticity times our cross-sectional area. So now let's do the same thing, but let's do it for a moment right here. So now we're going to find the strain energy for an external moment right now. So our normal stress, we can still calculate down here. If we look at our diagram below, there's our external moment there. There's our element, our d sub a right there. There's a stress at that element, some distance x right there along our x-axis right there. And we can see that this element right here is located some distance y off of our neutral axis. So our governing equation for our normal stress for an external moment is given by this relationship here. There's sigma sub x is equal to negative m, our moment right there, times that distance y, which is the location of our element from our neutral axis, divided by our I right there, and don't forget our negative sign. So now if we go to our strain energy right here is equal to the integral over our volume of our sigma squared over 2E, modulus elasticity, dV. Well, we have a value for sigma, so we can plug this in right here. So we'll do that, and what we'll see now is that our strain energy is equal to the integral over our volume right there of 1 over 2E right here, 2 times our modulus elasticity, times now when we plug in for our normal stress right here, my over I squared term from our squared term there, dV. So this is now our strain energy for an external moment M. So now, if we take a look again still at the strain energy for this external moment M, and we want to find a differential volume right now, because right now it's dV. Well, let's go back to like we did in that previous example right there, and we'll say that now our dV is equal to dA dx. So the normal stress varies in the cross section dA right there. So it's going to vary in there. And it's also going to vary along the length as mx dx right there. So it's also going to vary along this here. So it's going to vary within the cross section. This is your whole cross section right here. So it's going to vary by its location there. And it's also going to vary along this x-axis right here like that. And that's a realistic situation. It's not going to be constant through the whole thing. So defining this differential volume is going to allow us to calculate those. So now continuing on with the strain energy for our external moment M right here, if we take a look at this differential volume that we defined in the previous slide right there, if we want to take a look at our strain energy for the volume right there, and we have the differential volume that dV is equal to dA dx by that relationship right there, then what we can do is we go back to our general equation right here for strain energy. So again, we see this is with respect to volume right here. So we have our strain energy is equal to the integral over our volume of 1 over 2E, our modulus of elasticity, times, then we plugged in our value for our stress there, my over I squared dV. Well, let's replace this dV with a dA dx right there. So we can do that there, and what we can see now that we have, when we do that, this is the integral from 0 to A and L right there of m squared over 2EI squared times our y squared dA dx there. Well, we need to simplify this down a little bit more right there. Let's get a double integral out of this right now. So we come down here, and what we can see now is our strain energy is equal to, now if we deal with each of these right here, the integral from 0 to L right there over the length in our x direction right there, starting at 0 going out to a total distance L right there of our m squared over our 2EI squared. Now this is times, there's our second integral right there, the integral of y squared dA, and this is all dx right there. So now what we can do is we can reduce this down a little bit more, do out a little bit of calculus right there, and what we see when we reduce this down, we come up with this final relationship right there, that our strain energy for an external moment M is equal to the integral from 0 to L right there of our mx squared, so now it's dependent on that distance x right there, all over 2EI dx. So now this is all going to be dependent upon where you are in the x direction right here for this integral for where we have our strain energy, calculating our strain energy for this external moment. So now let's look at another case here. We're taking a look at calculating our strain energy for an external shear force V right here. So we have this transverse shear force is going to be applied. So therefore we have down here in our equation, there's our transverse shear force, our V right there. Again, this is going to be our area right here, cross-sectional area right there. There's our dA, our element right there. We can see there's our shear stress of that element right there. There's our distance from our neutral axis. There's our distance along our x-axis right there. So our shear stress is given by the equation right here. The shear stress is equal to that shear force times Q over our IT right there. So we can then look at this now and say, okay, for our shear energy, or sorry, our strain energy right here, our use of I, we have the integral over volume right here of that shear stress all over 2 times our moles of rigidity right here, dV. So let's plug in this relationship here for our shear stress into our strain energy equation right there. And when we do that, we end up with this relationship here that our strain energy is equal to the integral over our volume right here of now when we plug this in for our shear stress up top, there's our shear stress right there, squared all over this 2G dV. So we can do the same thing now for strain energy for our shear force right here, V. We can define a volume right there. So our dV is equal to dA dx. So the shear stress will be different at different areas right here, dA. Depending on where that dA is, this shear stress is going to be different and change based upon that there. So now that we've defined that dV is equal to dA dx, we can go with our general equation for our strain energy we saw on our slide before for our external shear force V. So our strain energy is equal to the integral over our volume of this Vx over IT squared, right there from our shear stress divided by 2G dV. So now we can plug in that dV is equal to dA dx. So now this is an integral over L from 0 to L right there of V squared over 2GI squared times the integral now for our area portion of this right here, integral over area of Q squared over T squared dA dx. So now we can simplify that down there and we say that our strain energy is equal to the integral from 0 to L of our Fs times Vx squared all over 2GA. We can see again, this is with respect to that distance x right there. Well, what is our Fs? So we have a definition for our Fs. Our Fs is equal to, relating back to area right here, our A over I squared times the integral of over A right there of Q squared over T squared dA, which is from up above there. So we've just plugged this in as an Fs as we write this out right here. So we could solve this separately and plug in here for a lot of those different types of problems. So now let's take a look at the same thing for our strain energy calculation, but now for when a torsional moment is applied right there. So we have our general equation for our shear stress, that our tau right here, our shear stress is equal to that torque right there, our T times our rho over V right there. And we have our differential, our dV is equal to dA dx right there. So we have all the relationship kind of condensed to one slide right now as we're dealing with this for our applied torsional moment. Take a look at our given diagram down here. There's our differential element right there. There's that distance from our neutral axis. That's our rho value right there. And there's our shear right there. And this is at some distance x along our x-axis right there. And there you can see that external torsional moment being applied there. So now with that information there, we're going to calculate our strain energy for that applied torsion right there. So it's still going to be the strain energy over volume equation at first right here. So we have this relationship right here that our strain energy is equal to the integral over volume of that torque times that rho, that distance to from our neutral axis to our element there, all over J squared divided by 2 times our modulus of rigidity right here, dV. So then we had that relationship for dV that we could plug in there. So now this reduces down to our integral from 0 to L when we plug in that relationship for our dV times T squared over 2G J squared times now the integral over the area portion of this here, which there's that distance rho squared dA dx. So from that there, we can reduce this down and say that our strain energy for this external applied torsion right there is going to be equal to our integral from 0 to L of this Tx squared. There's our distance right there that we're relative to right there as it moves along that, all over 2GJ dx. Now, there is the case for a constant torque along the length. So if that torque remains constant along the entire length and doesn't change, then we can reduce this down that our strain energy right here is equal to T squared L all divided by 2GJ. But again, this is just for that constant torque along the length. So now let's take a look at an example problem here. So in this problem here, they ask us to determine the deflection at the center. So we're dealing with the center of this here. We know the distance, the location of a centrally loaded beam. So we can see that in our diagram below. So we can see this down here. There's our figure 5.16. There's a centrally loaded beam right there at P right there. And if the whole beam is L, this is L over 2 where it's centrally loaded right there. And we want to find the deflection at that point as well. So we can see, well, if this is P right there, then we got a P over 2 and a P over 2 for our supports right there. We can see the dimensions of this beam right here is a width of B and a height of H right there, and we can see we're going to be moving some distance X along this from this end over here, and it's going to have some cross-sectional, some thickness here at the cross-section right here of a dx. So we want to determine the deflection. So we're going to deflection equation. So from here, what we want to do is take all this information from the problem statement right here. So we say, well, what's known? Well, it's a simply supported rectangular beam of known geometry. It is centrally loaded with the given concentrated force right there, and we want to find the deflection at the center of the beam. So let's create our setup page with that information. So as we create our setup page here, this is sample problem 5.4. And if this was a homework problem, you'd have your name up here, the due date, what assignment it was. So then we create our given information. Well, we know it's a rectangular beam and we know it's centrally loaded. So I redraw my diagram here, and I want to find the deflection at the center of the beam. We can see the center of the beam is L over 2. The total length is L. There's our centrally loaded point right there. P right there is our load at that center point right there. Here's our simply supported. There's our P over 2 and our P over 2. Here's our dimensions, our B and our H right there. So what are we going to assume? Well, in order to solve this problem and find the deflection at the center right there, we're going to assume that deflections are elastic right there. So as we begin our solution, what is our procedure for analysis? So we think about this here. Well, we're going to compute our energy, and then we're going to take the partial derivative to get our deflection right there. So let's take a look and go through this solution now. So if we think about this problem, we realize the beam is going to experience two different kinds of loading. It's going to experience bending and it's going to experience shear with magnitudes at any point x. So x again is this distance along our diagram up here. So this is why it's great to have this diagram to get a visual of what we're doing along the way. So let's take a look and define now what is our bending and our shear. Well, again, our bending is going to be our m, depending upon our distance right there, P2 over x, and our shear is just going to be that P over 2 right there that we're seeing in our diagram there. So that is our loading right there for our bending and our shear. So let's talk a little bit more about this bending right here. So we define our moment. We have that force times the perpendicular distance. So in this case here, our force is P over 2 and our perpendicular distance is x. So we have the m is equal to Px over 2. Now, this is only going to be valid between x is equal to 0 and x is equal to L over 2. We need to recognize, as we can see pretty clearly in our diagram right there, that this beam is going to be symmetric about the center. So that means that the energy in the left and the right half of this beam are going to be equal. So therefore, we can account for this bending energy by integrating between our 0 and our L over 2 and then doubling it at the end. So we can recognize the symmetry in this beam right here and simplify down our solution slightly utilizing this. So let's go back and revisit table 5.3 in our textbook right here. So again, this table here has a summary of our energy and deflection equations that we can use as our governing equations right here for the different load types. Now the load types that we're looking at for this problem right here are bending and shear. So for bending, we can see that we have this relationship here involving the factors of M, E, and I, where we have our equation over here, our U is equal to M squared L over 2EI. And for shear, again, we have this relationship here involving V, G, and A, our shear force, modular rigidity, and our cross-sectional area A right there. So U is equal to our 3V squared L over 5GA. So again, this goes back to getting our governing equations from table 5.3 in our textbook. So we do that. We went to table 5.3. So for bending, we have this relationship here. We have U is equal to M squared L over 2EI. And for shear, we have the relationship here that U is equal to 3V squared L over 5GA right there. So now what we want to do is come up with a general energy equation. So our general energy equation is going to involve both those because we have both bending and shear in this problem here. So we can say that U is equal to 2 times, again, this is 2 from what we just discussed before, because this is symmetric right there from 0 to L over 2 right there, times our equation up here now. We have M squared over 2EI dx. So this is relative to x right there. And then for shear right here, we have our relationship that we have the integral from 0 to L of our 3V squared over 5GA dx right there. So now we have the relationship we saw at the beginning right here, where our moment right here is equal to P over 2x. That's just taking the force times that perpendicular distance for half of the beam right there. And our shear was P over 2 right there. So we can plug both of those relationships we had at the beginning of our problem into this governing general equation for energy right there. So now we have that U is equal to 2 times the integral from 0 to L over 2 of, now we have on the numerator right here instead of m, we have p over 2x squared right there, all over 2 ei dx, plus the integral from 0 to L of 3. We'll replace that v with a p over 2 squared right there in this relationship here, all over 5ga dx. Now we can simplify things down a little bit here, and what we end up with is u is equal to 2 times the integral from 0 to L over 2 times, when we do our squared term out right here, now what we can see is we square the bottom there is 4, so this now becomes an 8 right there. So then we're going to have p squared x squared over 8 ei dx. Plus now we still have the same thing that we carried down from above, where we plugged in for our v at p over 2 there. So we now can reduce this down a little bit more, and we see that u is equal to 2 times the integral from 0 to L over 2 of p squared x squared all over 8 ei dx, plus the integral from 0 to L of 3 p squared all over 20 ga dx right there. So we can continue on to this, and the next thing that we want to do is we want to pull out our constants in front of the integrals right there. So u is equal to 2 over 8 times p squared over ei. So those are all constants we can pull out of the integral now from 0 to L over 2 of x squared dx. Well, that's a lot easier for us to solve. Then we pull out the constants on the other side right here. This is 3p squared over 20ga, all over the integral from 0 to L of dx. Well, those are two pretty simple integrals to solve. We can solve those out by hand. So let's integrate right there. So we do their integration out, and we now see that we have u is equal to 1/4 p squared all over 4ei. So that's just taking the 1/8 and saying that, or 2/8 is equal to 1/4 right there. This is still p squared over ei times, we do out the integral of x squared dx. Well, this is 1/3 x to the 3rd power right there cubed. So then we can say this is evaluated now from our limits integration from 0 to L over 2 right there. Then we do the same thing over here. Here's just our constants out front still, and the integral from 0 to L of dx is x evaluated from 0 to L right there. So let's move things around and distribute these through. And what we end up with is u is equal to 1/4 p squared over ei times 1/3. Now this is L over 2 cubed minus 0 right there when we plug those in. Plug in our limits right there. Plus, now we deal here, here's our constants right here, our 3p squared over 20ga right there, times now L minus 0 when we plug these guys in right there. So we can reduce this down, simplify it a little bit more. That goes away right there. So now we're left with u is equal to 1/4 p squared ei times 1/3 times L. When we distribute this to cubed right there, L cubed over 8. Plus over here, this 0 goes away right there. So we're left with 3p squared over 20ga times L right there. So now we can move this around, rearrange, simplify a little bit more. So we have 1/4 times 1/3 times L cubed over 8 times p squared over ei, plus, combine this all together, 3p squared L over 2ga. Let's combine all these guys now. We have 1 over 96 times L cubed p squared over ei right there. Plus, now this stays the same over here, 3p squared L over 20ga. So now what we have here, when we put this 96 over there, we have that u is equal to p squared L cubed over 96 ei plus our 3p squared L over 20 ga. So as we mentioned before, our procedure for analysis, what we're going to do next is take the partial derivative of this right here to obtain our deflection. So we have this relationship here that our deflection is equal to the partial of our u with respect to p right there. So we do that right there. Delta is equal d over dp right there of that whole value for u, which is our p squared L squared over 96 ei plus 3p squared L over 20ga. So now we see the importance of why we want to simplify this down. Doing that partial out when it was a larger term like that would not have been great. So we can do that, and we rearrange this here. So we can say now our delta is equal to our partial right here of, now we separate this just a little bit and change it right here. So we get our p's outside of that there. So all we've done is pull out our p squared and our p squared from this right here. So now it's a little bit easier for us to see, okay, what's a constant, what's our variable right there. So we're integrating with respect to p. For partial respect to p right there. So we pull out our p squared just as we did there. Then we can say there's one for each of those, so we can pull it out in front right now. So delta is equal to partial right there, and now our p squared is out front, plus of our L cubed over 96 ei plus 3L over 20 ga right there. So now the next step, we can reduce it down a little bit more and simplify it down a little bit more. So we can pull out a couple more variables right here, and we can see, well, we can deal with this right here. once we take our partial of this right here, we can say our p squared becomes a 2p right there. P squared becomes 2p right there. So there's our 2p, there's our 2p after we've taken the partial with respect to p right there. So the 2 cancels with the 96, the 2 cancels with the 20 down there, reduces down, and says that our delta right here is equal to PL cubed over 48 EI when we cancel out the 2 after our partial right there, plus 3PL over 10 when we canceled out with our 20 with our 2 right there, GA. So this is our relationship now for delta.